The Post Office has a large and increasing interest in monolithic integrated circuits for its telecommunications network. To assist designers of large-scale integrated circuits, the microtechnology unit has been equipped to fabricate small batches which can be used by system engineers to validate their designs before they proceed to large-scale production. One of the major problems facing both the circuit designer and the process engineer is the locating and rectifying of faults which prevent integrated circuits from functioning correctly. A typical integrated circuit, some 3.5 millimeters square, is illustrated here. This read-only memory contains about 1,600 active components interconnected by metal tracks. 8 input terminals may be identified here, and the same number of outputs are located here. On the right is the address control, and the remaining terminals are used to supply the electrical power. Within the integrated circuit, this red area decodes the incoming signal. A larger area to the right, and shaded yellow, contains the memory, whilst the blue region at the bottom is the output section. One of these devices will now be used to demonstrate a new technique for examining circuits under dynamic conditions. The silicon chip containing the integrated circuit is inserted in a scanning electron microscope, and arrangements are made to activate the circuit by a series of electrical impulses. Used in its normal mode, the electron microscope projects an enlarged picture of the integrated circuit onto the viewing screen. The contrast of this picture is greatly modified, however, if the electrical potential of the circuit is varied. For example, in this picture, the negative supply rail can be readily identified by their extra brightness. It is the use of this effect which will be demonstrated. The read-only memory is now being activated, and the changing potentials of the various stages may be followed by observing the variations in picture brightness. By slowing down the speed, it is possible to examine the operation in more detail. And in this particular circuit, the action of the memory cells can be more clearly observed by an adjustment to the address code. The normal facilities of the electron microscope provide the opportunity to examine any chosen area in great detail. The device you have seen in operation is an example of a good component. It will now be removed from the microscope and replaced by one which is known to contain a fault. Using the same technique as before, it is observed that the chip operates normally until it reaches a certain function, and then it stops. To make this clear, we will repeat the action, and you will observe that the circuit has again come to a halt. If now we examine the input terminals, we see that although the signal is present on this wire, the bonding pad remains dark, indicating a fault condition. This situation may be compared with a good connection seen here. In the faulty case, a residual oxide layer on the bonding pad is responsible for the electrical isolation. It is hoped that this simple demonstration will have conveyed some idea of the potential of this new technique, which is expected to play a major role in the development of microtechnology in the research department.